We are starting our last session for today. As a treat for you, as promised, we wanted to do something besides linear regression models. And this is what we are sort of taking a quick look at today in the form of variational autoencoders. And this will be sort of a relatively quick sneak peek into variational autoencoders, because it's also going to be part of the session on generative models that you will have tomorrow. So it's just to give you a flavor and a bit of intuition about what you can do besides linear regression. So very briefly, so the type of models that we are considering now is, if you recall Celia's slides from yesterday or presentation from yesterday where she talked about factor analysis, where we have a model specification where we are trying to model the latent space in which the data is actually living, and then the data itself is manifestations of that space. So in terms of sort of our graphical model specification, this is sort of what we have up here. We have n different data instances, and each data instance is characterized by a point in latent space. So this could, for instance, be a 2, 3, 100-dimensional distribution or a space that we have up here. And xi here is then our data. And the type of data that we're going to look at today, or to look at this afternoon here, are images. So that would be the MNIST data set that I guess all of you or most of you are familiar with. And then we are going to see how we can use these models here to get a representation of the images, a compact representation of the images in the form of their position, their representation in the latent space up here. And we also see how we can use these models to generate new images, like you sample a point and set, and then you're generating an image down here. So this is the setup that we have. We'll also assume that set I up here, and for the rest of this talk, you can just assume that it contains, it's two-dimensional. It's given a standard Gaussian distribution where these two variables are not correlated. So it's just a multivariate, two-dimensional multivariate distribution with a diagonal covariance matrix. Xi here is now a function of set I, but rather than having it linear, we allow it to be nonlinear, and the way that we implement this nonlinearity is through a neural network or a deep neural network. And xi in itself here are now given by Bernoulli distributions, are given as a Bernoulli distribution. And for our images, if we go back to that, that means that each pixel is either on or off, and that's then each pixel that's represented by a Bernoulli distribution. So our images, which are 28 times 28, will then be unfolded into a vector of size 784, I believe. And each of these elements in the vector then follows this Bernoulli distribution. Our neural network G is also called, we refer to that as our decoder network, so it decodes from the latent space down to our data space. It also has a bunch of parameters, weights, and here we'll just cheat and then look at point estimates of these parameters. You could also take a Bayesian perspective here and try to find a posterior distribution over those, but we don't do that here. Now, for doing inference, we will again rely on variational inference, because what we would be interested in here is to calculate the posterior distribution over latent space for each of our data points, and that also involves doing this nasty integration down here, which doesn't become simpler when you start to introduce a neural network in describing the connection between the latent space and the data space. And our initial plan here is to define a variational distribution, just as we've done previously today, one for each of our data points here. So I indexes our data points, our different images, and we would then be having a variational parameters for each of the images, and then finding a variational posterior distribution for these images. So that's sort of our initial plan, at least. Yeah? Why the... Yeah?
They have the same index I
So for each data point, we are going to calculate a point in latent space. So for each data point, you also have a latent variable and a observed data variable, and that's what the I index is here. Yes. So and this variational distribution that we have here, this is sort of what we have indicated here with the dashed line, that now we are doing inference in this direction. Yeah.
Just a question regarding notation. Do we only use plates to indicate the IAG sample, or because there were examples in the exercise when they used when we had like several parameters of the logistic regression, which were also random variables, so they were also put to plates.
Yes. There would be different ways of handling this specification, the exercises. It should probably not, for ease of readability, it would have been helpful not to put it in a plate notation there. One can do it, but there would be a nicer way of doing it. But maybe we can return to the exercises after this, because I'm afraid we don't have sufficient time. Maybe we can take it when we start the next exercise session.
Yeah, the question was like, what's the correct, or more, the correct notation? You use plates only for like samples, right?
Yes. Sorry, I'm not sure.
Rectangle to indicate the sampling of.
So here I'm using this plate notation, the rectangle out here, to indicate that we have a repetition of these variables. So we have the index from I equals 1 up to n, indicating that we have n replica of these set x variables. So we have set 1 x1, set 2 x2, and so forth up to n. And this is what this is simply, in this case here, syntactic sugar, indicating with a shorthand notation that we have a model that is replicated with an internal structure that is being replicated. Okay. Other questions here?
So you don't use plate to like indicate dimensions of x?
No, here we are just, the dimensions are fixed, so this is again the general notation, but we will be using a two-dimensional latent space, and then this, I believe, 28 times 28, 784 dimensions data space. Okay. Good. And just we are here, our initial idea from the top of our head would be to simply specify a variational distribution for each data point, so that we can, for each data point, find a variational distribution over its corresponding latent variables. So for xi, data point xi, we're looking at the variational distribution over zi. Now, if we do that, then we follow the methods that we considered just before the break. We specify our elbow function here. We use all our trig score function, reprioritization, what have we, and then we could start to learn. The problem here is that this is not really scalable, because if we have one set of two variational parameters, the mean and standard deviation for each of our data points here, and we have n data points, then the number of variational parameters grows with the number of data points that we have. So it grows linearly, but still it grows quite fast. So this is not really a scalable way of doing our learning. So a better plan that we are, or hopefully a better plan, is that we will assume here that the connection between Z and X, so this that we encoded using a nonlinear neural network, is somewhat smooth, in the sense that if we assume in our latent space that Zi and Zj, so two different points in latent space, are somewhat close, well, then they are probably also pretty close in the data space. So this is sort of some kind of smoothness assumption that we associate with our decoder network. So we could then also extend that and assume that there exists another smooth function, now h of x, that simply provides us with our variational parameters for our data, for our ith data case. So h takes a data point and returns our variational parameters for that data point. So the neat thing here is that if we do it like this, then we only need to learn the parameters, the weights that goes into this representation here. And if we represent H as a learnable function in the form of a neural network, then the weights are fixed that we need to learn, so the weights that are basically parameterizing our neural network. And so we have a fixed set of weights that we are learning instead of a variable set of weights, lambda I here, that grows with our number of data points. And this HXI here will now play the role of our so-called encoder network, mapping from our data space back into the latent space. This trick here is also this way of handling, of parameterizing your variational distributions with encoder networks that takes the input and provides variational parameters is also called amortized inference, in the sense that we are here not trying to, the number of variational parameters is not growing with the number of data points that we have. So it's fixed and it's given by the number of weights or the weights that we have in our encoder network. And this approach of doing variational inference is also something that you see in many places also outside variational autoencoders. So this is sort of really a thing to bear in the back of your mind, that this is something much more general than the class of models that we see here. So besides the number of parameters that I already mentioned, then there are also other things to note. For instance here, that if we have some kind of regularity in our, or smoothness in our encoder function, then we also have some kind of regularization during learning. And here we are not really changing the model, we are only changing the parameterization of our variational distributions, not the model in itself. So let's try to continue a bit with this. So now we have a full variational autoencoder approach. We have our model over here. We have our parameterization of our different distributions up here. And our goal is now to maximize both the parameters that goes into the decoder network, that's W, and in the encoder network, that's lambda. And here we are using notation slightly because we refer to the weights of the neural network that represents our encoder network using the same notation as we use for the variational parameters that corresponds to that encoder network. So lambda here is basically referring to the variational parameters or the weight of the neural network providing the variational parameters. We'll use the same notation. And we then have our objective function here defined in terms of our elbow. For doing the actual learning here, we have the exact same setup as we have done for the rest of the day. We are increasing the elbow here by generating samples for calculating our gradients. These are noisy estimates of the gradients, but unbiased. And then we use these gradients here to optimize our elbow function with respect to both the parameters in the encoder network and the decoder network, and then we are iterating like this. Now, last slide here before the notebooks to illustrate this. So as I said, we are going to play around with the dataset, the MNIST dataset. So we are going to work with the dataset consists of 50,000 examples. We are going to use a subset of that to make it a bit more efficient. We have XI being a binarized, it's the binarized version of the MNIST dataset here, 784 pixels when expanded, and these here are some examples. Examples of encoder networks that one could use, and which you can try out, is a network like this, where you, for the encoder network, mapping from the data space to the latent space, here going through a relo to a hidden layer, to another hidden layer, then branching out and calculating the log of the, then calculating the standard deviation and the mean value that goes into the parameterization of the latent space. And for the decoder network, we could have something like this, where we are mapping from the latent space through a series of hidden layers down to the data space or the parameters of the data space, our Bernoulli distributions. And it's here the lockets that are being returned for the Bernoulli distribution. So, to give you an example of this, we have our variational autoencoder specification. And here we are getting the MNIST data set, and I'm only using a subset of it. So I think we are taking out 100 images for 3 different classes, 5, 6, and 7. If you want to use more digits, number of instances, or other digits, you can just change the values up here. But that's the default, just to get the ball rolling and get something relatively quick up. Here we are just visualizing an image. Too many sessions. Okay. Let's just try again. Okay. Cool. So, but how do I? And the students. Okay, let me just go back again here. Okay, I'm just doing this. Good. So here we are defining our variational autoencoder. So it's now implemented as a class. It takes takes 3 arguments here. Setdim, that's the dimensionality of our latent space. That's by default 2. It takes an encoder and a decoder, so that would be PyTorch neural networks that defines our encoder and the decoder. Here we have our model specification. So that was where the decoder came in. So we have everything here. We have a plate over our data points. For each data point, we create a latent variable set, and then we pass it through the decoder to get the lockets of the observation. So the data variables, the observations down here, defined as Bernoulli distributions. Down here we have our guide, where we have our encoder specification given, and here we are again having a plate over the data, where we are going from our encoding our data to latent space defined by a location, a mean, and a scale, a standard deviation, parameterizing a normal distribution. I haven't shown you the encoder and the decoder yet. That's just, that follows shortly. Then 2 functions here. One thing is that we want to play a bit around, so we can also sample images. So you pick points in latent space, and then you generate, here we first generate a mean image corresponding to that point, and below that we generate samples of different images from this data space. Here we are trying to reconstruct images. So what we do is to take an image, map it to latent space, calculate the mean in the latent space, and then mapping it back to the data space, and then we see, can we actually reconstruct the image that we just provided? So this is our definition of a variational autoencoder. The encoder that we use here is pretty simple, again, defined here as a PyTorch class with 2 hidden layers defined here and combined down here. So this is the encoder where we are mapping into latent space. We have a mean here and a scale here, passed through a soft plus function to ensure that we have positive values. And we have a decoder here that's even more simple. So this here is just a very simple linear decoder that maps from the data space down to, from the latent space down to the data space. Then we are more or less ready for doing the training. So this is this is one training step that we are taking, calculating the loss. And here we are setting things up for doing the actual training. We have a specification of the dimensionality of the latent space. 2, a learning rate. We have our variational autoencoder defined up here with the specification of the dimensionality of the hidden layer here. 1,000 iterations or epochs, clearing the parameter store. Otherwise, everything is as you just saw before the break, so there's nothing really interesting here. And now we are doing the learning. So what we are outputting here is for each 500 iterations, we are plotting images and then trying to reconstruct them again. So this is an image, this is the reconstructed image. So this here is just before we do any learning, and it's just random noise that we have here. After 500 iterations, things start to look better. Now you have something that seems to be slightly more recognizable in terms of digits. Something now after 1,000 iterations, things look even better. Still, it's a bit blurred, but it's not completely off. And we can also see here that our elbow is sort of nicely increasing, so we should be quite happy. We can also start here to maybe do a bit of exploration of our latent space. So this is what we have here. So now we are taking all the images, putting it into latent space. The color coding here represents the 3 types of digits that we have, and we can see that at least for some of the digits we have an okay separation, but there's also quite an overlap between the blue and the orange part. Another thing that we can attempt is to try to visualize our latent space. So what we do here, what this visualization here shows is our 2-dimensional latent space now placed out in a rectangle, and then we are dividing it up into cells. And then we are generating images for each of the cells. So we are picking a value and then generating an image for it. That's sort of roughly the way that it's being done here. And this is the result that we get. And this is not that nice. So in particular, you can see here that the top part really doesn't make that much sense. So when you start to look at the lower part, now things look somewhat more recognizable. You have some 7s down here, 6s, and then you have some 5s over here also. But if we go back to the previous figure here, what we can also see is that whereas set0 seems to be really being exploited, that you have different values, that the range of set0 is being exploited, the same doesn't hold for set1, so they're all negative values. So that would also correspond to mean that the top part of the latent space, so to say, so this part up here, is not really being used by our variational autoencoder. And this is one of the reasons is that our encoder and decoder networks are simply too simple. So we need something more fancy in order for us to be able to really learn something that is a bit more meaningful here. And here we can also look at some posterior plots, some density curves. So what we should do now, and the question is whether we have sufficient time for this. Should we spend 15 minutes? 15 minutes on an exercise, just a second, where you should try to implement a fancy encoder and decoder. And we have some a skeleton here for you to fill in. Maybe it's easy just to start off and copy the code from our simple encoder-decoder networks in here, and then see what you get. And then you could try to add a bit of a bit more complexity to these models here, and see what you end up with. But this is sort of the idea. And we just had a question.
It was about what fancy was, but I guess.
Okay. So this is precisely the fancy part. So there are things to fill in here, but maybe just start out with the simple encoder-decoder models. And below there is additional code that you can simply, once you fill that in, additional code that you can run to get some hopefully nice visualizations of the results. And we have around 15 minutes for this, and then we'll just spend 5 minutes doing a bit of recap where we can show you one possible solution for this. Okay, it's time to get started again. So, time flies when you have fun. We only have 10 minutes left of this session here, so I'm just going to give you a illustration of one candidate solution, and then we're wrapping up with some concluding remarks. Our departure point for the exercise was that we had sort of this not very convincing representation of the latent space. So could we do something better? And I've been around and we can see that many of you have actually come up with some very nice solutions. One candidate solution was given in the slides. So an encoder network illustrated like this and a decoder network illustrated like this with two hidden layers. And this is what we have implemented in our candidate solution that you'll see. So this here is basically just a one-to-one mapping between the illustrations in the slide and our Pyro or PyTorch code here for the encoder and the decoder. And I have already taken the liberty, and here we have the learning part, and this is identical to what we had before, except that we now have replaced our encoder with a more fancy one. And if you run this, and I have already done that, so now you just get the output, then we see sort of also a nicer progression. We start off sort of where it's completely blurry. After 500 iterations or epochs, we have something like this. Again, these here are grayscale, so we are reconstructing the top row down the bottom row. It's grayscale because we are taking the mean value of the Bernoulli variables. Then we get something even sharper here, and again, we still see a nice convergence in terms of elbow. But the results here are some pretty good. If we explore the latent space, so here we have, I'm plotting both the standard variational encoder, plot the latent space of the standard variational autoencoder we started out with, and the non-linear fancy version. So this is where we started with, and this here is our new one, where we see up here we have quite an overlap between the orange and the blue class. Down here we have still have an overlap, but a much nicer separation. If we explore the latent space that we were not too happy with before, so this is again, this here is again where we started with, where we saw that in particular the top part was not really being used, it didn't really make sense. If we now see what we get here, okay, there's still something up here at the very top left corner that could have been nicer, maybe a few more iterations could have helped, but otherwise we have a much more crisp representation. And again, what we see here is our two-dimensional latent space, sampling a point from that, mapping it down to the data space, and providing the mean value in the latent space for the Bernoulli distributed variables. So, example of a generative model here. And also in terms of the contour plots, we see this nice separation. Here are a few more reconstructed images, but I don't think we need to look at that. So that was sort of the promised illustration of something a bit more fancy than a Bayesian linear regression model. And as you can see, you can basically combine in a nice way both the generative model with more sophisticated neural network for added expressibility, and all being driven by the underlying PyTorch, Pyro machinery for doing the calculations. Everything here wrapped up in a variational inference setting for also doing uncertainty estimation. Good. I think that was more the last part on the variational autoencoder. Are there any questions before we come to the concluding remarks here? Yes?
After this mapping of encoder to the latent space, then we do this resampling, right? And what's the relation of this to the parameterization?
Here, there's actually, are you here referring to the way that we do the visualization, the reconstruction here? So here there would be sort of no more connection besides sort of the way that Andrés presented about using the reparameterization trick, where you're doing where you are having the, where you are simply sampling from a standard simple distribution and then having everything reparameterized through a deterministic function. So there's nothing.
In this case, the deterministic function is a neural network.
So
the encoder network is a deterministic function.
So besides that, there's nothing sort of in particular. We are not introducing any new machinery here. So everything is as you've seen before the break in terms of the underlying machinery. Are you here talking in terms of calculating gradients? Or are we in terms of doing the visualization?
We get the image, we map it with the encoder to the latent space, then we resample it.
Oh, yeah, so maybe I wasn't clear. So that resampling and mapping it down again, that has only been for illustration purposes. So to see whether does the encoder and the decoder network actually make sense. And here we don't sort of have plots like we had previous today to see that we can find some regression lines and the like. So it's okay. My apologies if I didn't quite. Other questions? Okay, then final remark, yes.
Gee, it's been a long day, and finally, recap and conclusions. So we'll do that quickly. We started off today by arguing that Bayesian machine learning is a good thing. The key point being that when we do this, we can maintain model uncertainty all the time, using that for downstream tasks. So this is a way to be more robust and more resilient when it comes to data noise and all that. The problem, though, would be managing this posterior. And therefore, we started with this variational stuff. I should say, once again, that this was casted in the setting of Bayesian machine learning in this talk, but that is not necessarily the case. So this is like the go-to machinery for any type of probabilistic AI stuff. Now, what we did now was to try to approximate the posterior because we were doing Bayesian machine learning, but it could have been different stuff, as I say. The objective here was to find the approximation that was closest to our target in terms of the Kullback-Leibler, which we then remapped into the elbow stuff, right? So when you hear about elbow or read about elbow in all these papers, then this is basically what's happening. We are thinking about the approximation that is closest to our target in terms of Kullback-Leibler, for better or worse. We talked about what that means and the good and the bad sides of that, like the zero enforcing. That is even stronger due to this mean field assumption that we make. So this is something to think about. The underestimation of the variance, I would say, is the biggest problem with the way that we are doing variational Bayes here. Then we saw different ways of solving the thing. Sometimes we can do this analytically. This is specifically for exponential family distributions. And when we can do this, then it's very efficient and very stable calculations. So whenever possible, to use CAVI or coordinate descent, you should. We have been struggling a bit with doing the derivations. There are also tools that does this for you, like variational message passing tool. What's the name of that tool? I forget. Yeah, like the amidst that Andrés and Thomas and I were. Inference. Yeah, there are several of these tools that are implementing variational message passing. So whenever possible, if you are happy with the conjugate exponential family, then this is the way forward. Scales very well. When not, then the gradient-based stuff that we've talked about after lunch is more powerful, more versatile, but also then less stable. So specifically being beware of the variance is important. The black box core score gradient stuff that we did first is really like floating around a bit. Lots of variance in the estimators there. You can't really always trust the results that you have. Reparameterization is helping whenever that is available, and mostly it would be. So then we have also seen Pyro. So probabilistic programming languages are now kind of the glue here. Silja talked yesterday about the build, compute, critique, repeat cycle, where we are continuously improving our model. And the PPLs are kind of helping us doing this efficiently, because we don't have to spend so much time on inference, we don't have to spend so much time on model validation stuff ourselves. The tools are there for us, and we can focus on doing the modeling and validating using the tools that are there. We have focused on Pyro, which is on top of PyTorch. There are other alternatives like TensorFlow. They have TensorFlow probability that also implements lots of these things. Infer.net is a popular candidate. Turing.jl is the alternative for those of you guys who prefer Julia, and so forth. So there are different alternatives there. And then finally, what next? So when we started doing this, Thomas, Andrés, and me, for like 10 years ago maybe, this was the research topic in itself. But now it is, if not maturing, then at least being more stable and more solid. And instead of being the thing to research, this is kind of the tool to use for doing your research. So it's a step on the maturity ladder, I would say. And even though there are lots of stuff to produce and to investigate further, we are now in a setting where we have a toolbox that is reaching maturity, which is nice. So our hope now today has been that we have been able to give you an understanding of the strengths and the weaknesses of the approach. And it's been a slightly too long day, I would say, but still we got through it in one way or the other. And yeah, we hope that you feel that you've learned something, and that you're now ready for the cool stuff that starts off tomorrow morning. So thank you.